Good morning. Let's get started. Today you may have noticed that I posted a copy of a manuscript that I am working on. It should be supposed to be published early next year, but it's a long way to go. There are lots of places I need to still put in my notes. And if you have any comments, please let me know. I'll be glad to hear from you. Also, I want to mention that do not cite the book because it's still not out there and it's still work in progress. Okay. And the second item I want to mention was that about the assignment. Leo said he is going to answer most of the questions you have posted today on the forum. And I will also go through them today. By end of the day, you'll be hearing from me or from Leo on the clarifications on the questions. And on most of the data related issues like R, importing commands from R and so on, I am not good at that. I would expect Leo to answer them. But if there are any conceptual questions, I will definitely get back to you. Okay. And before I get started, do you have any questions? Any questions? Okay. I think I would like to complete all the methodology part of it today. And I still have a couple of items I want to briefly mention about estimating volatility using high frequency data. And then we will get to second part of the lecture today is going to be on multiple time series modeling and co-integration techniques. And co-integration has become pretty popular in trading right now because people are looking at several stocks together. They would like to know which stocks are moving together, and extending the concept of pairs trading has become one of the important tools people are developing now. So I'm going to a little bit focus on multiple time series modeling, the second part of the course. Okay, and having said that, again the same caution applies here also. When it comes to financial time series, the structure tends to be fairly simple. Once you start differencing the series, there is not much left, and maybe in the short durations like high frequency data and the short duration tends to have some structure that you can exploit. Okay, so before I get to it, I think we talked about estimating volatility in two different contexts. One is the low frequency context, the other one was the medium frequency context. So today I want to briefly comment on how do you estimate volatility in the case of high frequency context. Okay, so just to give you an idea here, estimating volatility. So in the case of low frequency context, so the simple estimation would be estimating the return square and adding them up. That becomes the low frequency context. Here I think we talked about modeling explicitly using Garch models and so on. So this is for daily data. And then we also talked about for medium frequency. So if you have 10 minutes or 1 hour, 5 minutes, whatever the data that you have, here we talked about price bars. So which consist of open, close, low and high. So last time we talked about how to use these 4 different quantities and estimate the variance. Okay, and today I think I want to briefly comment on high frequency. Okay, in the case of high frequency, anytime the transaction occurs, it's possible that you may have a different price, but generally the prices tend to bounce around a small bid-ask spread. Okay, that's what moves around. Okay, still there is variation in the data. So most of the variation may come from what we call as market friction. It may not come from true change in prices. Okay, so when it comes to high frequency, I think there are two questions we want to talk about. One is, how do you estimate the volatility? In this case, we are going to call them as realized volatility. And the second part of it, I think, is important concept that I would like you to follow through is concept of sampling. Okay. So in statistics, we somehow tend to believe that having more data is better, but sometimes more data creates more noise. Okay. So you may miss the signal by creating this noise. Okay. So in order to reduce the noise, you need to smooth the data, and smoothing means that taking a certain interval and trying to compute some sort of summary measures for that interval. So the interval is too large, as I mentioned before, you may miss the variation, and if interval is too small, you may not be doing much to the variation, so you have to play between the two. Okay. So when we talk about realized volatility, I think here it is, it's given. Okay. Suppose you have monthly log return. This is an additional way of doing this, or otherwise if you are estimating daily return, and you can see the daily return is nothing but sum of various returns that take place during the day. So this could be daily return, this could be return for a minute or whatever you can call it. In any case, the idea is fairly simple. The idea is that you have return for the month and then you have the return for the day, and so you can show that if you are going to define the return as the cumulative return as the difference between the log prices, then we mentioned that cumulative return is nothing but just adding those returns. So how do you estimate the variance for the monthly return? The key here is the following. Variance of the monthly return could be consisting of two parts here. One is the slight simple variance that you would calculate. The second part of it is that it could be variance, the covariance between successive time points could be negative or positive depending upon the sign. Usually we see a negative correlation. So the idea being that if you have the process returns follow moving average process of order 1, you can show that the best way to compute this variance is not only just looking at the standard calculation of the variance, but also you need to account for the autocorrelation in the data. So that's the main part of this. Okay. So when you compute the variance, just don't use the usual concept of variance. The usual concept would be like, if you take away n, you can see this 1 over n minus 1, RTI minus R bar T squared is computed with the variance, right? So in addition to that, they are suggesting that you should also take into account the moving average term. That's the main part of it. Essentially, you are accounting for the autocorrelation in the data. Okay, so that's the main part that I wanted to mention here. I have something else in my So that is one part of it. I thought I had one other piece of notes that I wanted to show you. Just when you think you are best organized, I think, it's when you make the mistake. Anyway, I'll get back to it next time. Okay. The second part of it is the following. This is the crucial part of it, I think, So if you are going to take data of every transaction, it's going to increase noise in the data. Okay. If that is the case, how do you aggregate the data? The question, I think, is that is there an optimal time interval that you can use so that instead of looking at all the transactions, you want to look at some sort of average transaction per interval. Okay, that's the idea here. Okay, Before I get to this slide here, I'm still looking for my, so one nice comment I had, I don't know where I'll mention this later. Okay. So this is actually a very interesting concept, and there's lots of mathematics involved here, but I'm going to try to simplify this using some intuitive ideas here. So let's assume that the transactions take place from 0 to capital T. We know that in the high frequency context, ticks can occur at any point in time, right? Just for this illustration, I'm going to assume that it occurs regular intervals but more frequently. So I'm going to write this T1, just divide this into n equal parts. T1 is delta, T2 is 2 delta, and so on. And T is equal to T of n delta. So we all know that in the high frequency context, delta is very small and n is very large. Okay. So when you have this pricing process, P of T star is P of T minus 1 star plus, I'm going to write it, instead of putting the variance, I'm going to write it as sigma times epsilon T. And what is the usual assumption we make for epsilon T? Normally distributed with mean 0 and variance 1 because of the time unit being 1. In this case, we can say that the interval is of length delta. So I'm going to write this as, this is supposed to be normal with mean 0, and this is the length delta. Okay, this is the key part of it. Okay. But then I think we have transactions price, which is supposed to be true price plus some market friction A times UT. Remember, we talked about Rolle's critic. A could be the bid-ask bounce, or A could be just the meeting demand and supply. It can characterize any number of things. So I'm going to write UT follows normal with mean 0, standard deviation is 1. Okay. Okay. Suppose there is no microstructure noise, which means that there is no UT. What is the estimate that we want to come up with? So I'm going to write that no microstructure noise. So what I mean by that is there is no friction in the data, no microstructure noise. Okay. Then the usual estimate is that sigma hat T square is equal to 1 over T. I'm going to take this T off, just sigma hat squared 1 over T. This is going to be I, or just write I ranging from 1 to n, R of I square. I square. Okay. I didn't subtract R bar mainly because we all know that returns generally tend to be, average return tends to be around 0. So you can show that the expected value of this is nothing but, just by going through these calculations, you can show 1 over T times, there are n intervals, n times this expected value of Ri squared. Just based on this, you can show it's equal to sigma squared delta. Okay. And variance of this you can show In order to calculate the variance, you have to calculate the fourth moment and so on. You can show that variance of this is going to be 1 over t squared, I ranging from 1 to n, variance of Ri square. So this is nothing but n over t squared, because these variances are supposed to be, Ri squares are supposed to be independent, so variance is just adding up those n terms, and you can show that this is given as sigma to the power 4 delta squared. So this is, you can show this is equal to, 2 times that, okay, 2 times sigma to the power 4 delta divided by t, because we know that t is supposed to be n times delta, so when you carry this through, you should see that. Okay. So, so from here you can see the asymptotic variance of this quantity here is given as sigma hat squared minus sigma squared goes to normal distribution with mean 0, and that is the variance. Okay. And variance, as you can see, is given by this quantity here. Let me write here. Okay. W is equal to 2 sigma to the power 4 delta. Okay. So here is a key question for you. So your goal is to estimate the variance as precisely as you can, right? Which means that this W should be close to 0. To make W close to 0, you need to make delta to be close to 0. See, if there is no friction, you want to use all the data, right? Delta close to 0 means that's a real situation in the regular case. Okay? So you can show that, make a just right to make delta small, sample make small, selects delta small. Okay. Is that clear to you? Just simple, that's a traditional point of view, right? In order to make the variance more precise, take as many data points as you can. Okay. Now I think the observations are noisy, but ignored. Okay. So observations are noisy, but ignored. So essentially we are going to estimate the variance as usual and then check under the model when there is noise. Okay. So we know that the return is supposed to be P of t minus P of t minus 1. Okay. So we have done this calculation before many times. I'm just going to write it in the following form. This is nothing but sigma times epsilon t plus a times ut minus 1. Okay. So this is supposed to be independent process, and this is because of this minus ut minus 1. If you take the difference here, the successive differences are going to be correlated. So if you take a independent process and mix with moving average process, you can show that the resulting process also moving average process. So I'm going to write this is in this form. This is going to write it as Wt plus eta times Wt minus 1. So this becomes moving average process. So remember that the effect of market friction is to create this kind of dependence in the short duration. So that's how you get the moving average process in the returns term. Okay. So WTs are uncorrelated, which means 0 are uncorrelated. There is no reason to assume normality for any of these things, but if you want to test it out, that's when you need to have some distribution with mean 0 and variance. I'm going to write it as gamma square. Okay. So there are two things we started with. Sigma squared is the volatility, true volatility, and I'm going to write it as A squared. So this is the true volatility, this is the variance in the friction. Okay. Because of a little bit of reparametrization we have done here, we are going from here to gamma squared and this eta here. Okay. Eta is like the stickiness parameter, it's the moving average parameter that you have. Okay. So you can show the following just by going through the variance calculations. You can show that gamma squared plus 1 plus eta squared, which is nothing but the variance of RT, So this is equivalent to, in terms of original data, is equal to sigma squared delta plus 2a squared. Okay. Essentially going through the calculations that we did before, okay, sigma squared. And similarly, the covariance between RT and RT minus 1 is going to depend upon this eta here. So you can show that the covariance is given as gamma squared eta is equal to covariance between RT and RT minus 1. So this gives you minus A squared. Okay. So in terms of the variance, you can see, can show that if I write the proportion of the variance here, pi is equal to variance of the microstructure noise is going to be 2a squared sigma squared delta plus 2a squared. Okay. The 2a squared comes mainly because you can see I wrote it as ut minus 1. So when you take the variance of the term, you are going to get variance of ut is 1, variance of ut minus is 1, and then covariance is 0, so you get 2a squared. Okay, that is the proportion of variance. Okay, so let me write here. So you can see here, as delta goes to 0, what happens to this proportion here? As delta goes to 0, what happens to this proportion? Goes to 1. Okay. Essentially, if you sample too many times, microstructure noise is going to, variance in the microstructure noise is going to dominate. That's the key point. Okay. So as delta goes to 0, microstructure noise dominates. Dominates. Okay. So if you look at the eta itself, you can see eta is supposed to be, so covariance divided by the variance, you can show that eta is minus a squared divided by sigma squared delta plus 2a squared, and you can see It's minus 1 to 0. So there is a negative autocorrelation that you see in the data. Okay. I think the main point I wanted to make was this one here. By taking very frequently, I think data, you would see that microstructure noise is going to dominate. Okay. So in fact, you can show that in this kind of situation, remember when we wrote this expected value of sigma squared here, it tends to be unbiased, whereas here you can show expected value of delta sigma hat squared minus true variance sigma squared is given by 2a squared over delta. Okay. So if you make delta very small, what happens to this? Going to be very large. Can you see that? So this is going to have a large bias. Okay, and so this sort of gives you the bias term. Okay, and variance of sigma hat squared is a little bit complicated here. I'm not sure how else I can write this. Variance of this depends upon cumulative moments of the cumulants of this fourth moments and all that stuff. So I am not going to write, let me give it to you for the sake of completeness. I will give you a very good reference for this, so that if any of you are interested, you can take a look at this delta squared plus 4 times sigma squared delta a squared. It's pretty complex derivation, 6a4 plus 2 times fourth cumulant of u divided by t delta minus 2 times power 4 u divided by t squared. And you can see that if a is 0, all these things will simplify to where we started. Okay. So I think the question is that this is the bias and that is the variance. So if delta is small, which means that you sample as frequently as you want to, you can show that bias increases, variance comes down. So you need to somehow combine the two to see how do you combine the two. Okay. So what is the concept that combines the bias and variance? Let me push this up a little bit. What is the concept that combines the bias and variance? Anyone? The concept of mean square error. Mean square error is nothing but bias squared plus variance square. So please from here come here. Okay. So mean square error is equal to bias square plus variance. Okay. So if you want to minimize this, I think you have to do it at the expense of one or the other, but you can show that the optimal interval delta star is given as 2 times 2 to the power 3 a to the power 4 over 3. This is after doing a lot of simplification. This is sigma to the power 4 over 3. So this result is useful result. That's the reason I went through this. And the paper to read is by, hope I'm writing this properly, I. Shahalia Mikland and Zhang. I think it's 2006 paper that came in Review of Financial Studies. So they have series of papers on this topic, and most of them are pretty technical paper. And this one here is it's very well written, also gives you some intuitive background. And I'll try to post this paper. If it is not on the list already posted, just let me know. I'll post it for you. Okay, it's a very, very nice paper to read. Okay. So a couple of things I want you to keep in mind here. You can see that if there is no microstructure noise, you can pretty much delta star is going to be 0, right? You can sample as frequently as you can, right? And so it depends upon two things. One is this quantity here and this quantity here. So essentially it comes down to the following here. And you can see this is apart from the constants that you have, and t to the power 1/3. T is sort of fixed mainly because of trading hours are known to us. So this is given as a over sigma to the power 4/3. Okay, 3. That's what it comes down to. Okay. So one is this volatility here. Sigma squared is the volatility that you get. A is the microstructure noise. Okay. Okay. How do you estimate this A in practice? In order to get an idea how often you need to sample, right? You know the volatility of this sigma based on daily data. You can estimate that quantity, right? But how do you get a handle on this A? A is supposed to be the microstructure noise, right? How do you get that handle? Remember we talked about Rolle's critic, right? Rolle's model. Essentially it looks at, supposed to be the measure of Bida's bounds, right? So A is indirectly captured through Bida spread variations, and you get an estimate for A, and then use that estimate here, and you get an estimate of sigma based on daily data. So you take that ratio and go through the calculations. Okay. So in most cases, I think there is another paper by Bandy and Russell which kind of talks about expanding this idea. So they say that depending upon the variation in the data, usually 2-minute to 5-minute aggregation tend to work well. Okay. So you don't have to take every observation. Either you can sample every 2 minutes, or you can aggregate the data for 2-minute or 5-minute interval, then use that information to estimate the variance. The whole point of this exercise is to show that when you get the returns data that you saw before, so you want to take the returns such a way that the second part of it, ut minus 1, vanishes, right? That's the part that's giving you the trouble. Okay, you want to take it. So usually 2 minutes or 5 minutes interval, that's what they mention in the literature. Okay, so I'll try to post this article. I think I totally missed out. I should have posted before I came to the class. Okay, any question on it? Any question on it? Okay, so getting back to today's lecture, I think I want to wrap it up today so that we can start on the trading algorithms on. Okay. I'm going to talk about multivariate regression, multiple time series, co-integration, all these things in one sweep. So this is an area where I do active research. I know pretty much what's going on in this area. Okay, and but although I'm going to cover a little bit of general topics here, the ultimate goal is to get to co-integration. okay, because that's a concept that you're going to use, okay. But in the process, I think I need to go through some of these things, okay. How many of you have done multivariate regression before? Okay. I'll show you briefly, the main ideas here. So the main point of this exercise is to show that when you have large data sets, large number of variables on both sides, you get too many parameters that you have to estimate. So those numbers can be reduced through some sort of logic, and one is data dependent logic, the other is logic that comes from some theory, economic theory, or some theory that tells you that some of these coefficients are to be constrained to certain values, okay. So let me briefly set this up, and then I'll try to give you my intuition behind most of these concepts, okay. I think I want to use this here. So we are going to write the following. It's going to write this yt as a set of response variables, and there are m response variable yt, and then we have xt set of predictor variables n times 1, and there is this connecting matrix which is the regression coefficient matrix, which is of dimension m by n, and then you have this residual term which we are going to assume for the time being independent, and so on, okay. So this is a straight regression model. If you have m is equal to 1, this is a multiple regression model, and the key here is the following. In macroeconomic modeling, generally m is pretty large, say m is equal to 10, n is equal to 15. What is the dimension of this matrix C? How many numbers you have to estimate? 150 numbers, okay. You can see that this dimension gets pretty much out of hand very quickly. The dimension of m and n increases, okay. But in any case, how do you estimate this C matrix? I think I'm trying to do everything in terms of C concept here. So there are m variables here, there are n variables here, okay. So in the form of matrices, I don't want to rewrite everything what's given here. In the form of matrices, we are going to have take data matrices y and x. Y matrix is nothing but taking the response variable information and stacking up to capital time t, and then x is same as taking the x variable, stacking up to xt. So because of that, the dimension of these matrices are going to be m by t and n by t. So more precisely, you can write it in this form: y is equal to c of x plus epsilon here, and then I think rest of the calculations follow from least square estimation, okay. So you can see that after you stack up the data and write it in the matrix form, you can see that y is equal to c times x plus random quantity here. So dimensions are given as m by t, this is m by n, n by t, this is m by t. So least square estimates, I think if you remember, your regression is nothing but multiplying, just taking y minus c of x and differentiating with respect to c. That results in the following. It's nothing but y times x prime is equal to c times x prime, and x prime and this error term are supposed to be uncorrelated, so it gets dropped out. So essentially you can see this dimension here is m by n, and this dimension is n by n. So from here you can see x prime is supposed to be positive definite matrix, and this gives you C is equal to y x prime times x prime inverse. So that is the least square estimate that you get. Okay, nothing but just post multiplying this equation by x prime and then using this concept here. Okay. So many of you have seen the problem of multicollinearity. What exactly is multicollinearity? Multicollinearity occurs when the predictor variables are highly correlated, right? So which means that this x prime could be not invertible, so this condition may not be holding true. Okay, so but here I think we are not talking about multicollinearity, we are talking about common relationship among this between y and x. Okay, this is your C tilde matrix. That's how you get this matrix here, and then you can estimate the error covariance matrix that we talked about using this residual covariance matrix. Okay. But the comment I have at the end of the slide is the most important one. Okay. What does it say? It says that multivariate regression is nothing but series of multiple regression. Okay. So you have this m predictor variables, right? M response variable, n predictor variables. What it says is that you take one response variable at a time, run a multiple regression, get the coefficients, that becomes the first row of that matrix. Take the second response variable, run the regression on n predictors, that becomes the second coefficient, and so on. Okay. So essentially there is no real multivariate feature that comes into play unless there is some constraints on the coefficient matrix. Okay. So in practice, how would you reduce the dimension of C? If you are going to estimate, say in the case of macroeconomic variables, there are going to be 150 coefficients. First of all, you may not have enough data to go around to estimate that number. How else you can reduce the dimension? Okay, that's it. Rank is one option, but usually when you run the regression, how do you reduce the number of predictors in the regression setup? Some greedy approach is that you run the regression and see which coefficients are not significant, you drop them, you do stepwise regression and all these other regressions that are being used, right? So, so I think that's one approach that people have taken, but in the case of multivariate regression, if there are constraints on this coefficient matrix, you can't just look at only one at a time, right? You have to look at jointly. So that's the main idea that I want to briefly mention here. Okay, so they have some in the multi-factor asset pricing models. Okay, you can show that. So the left hand side is the return. Okay, and right hand side is supposed to be the factors. So if you have a CAPM model, the right hand side factor is going to be the market factor, and if you have Pharma and French model, it's going to be market factor plus book to market ratio and one other factor. So I think the model here can be used in the context of asset pricing models. I think it's very useful. So there is also, I think, in addition to looking at co-integration, one other aspect of this model that we are going to use is in what we call as fair value models. Okay, it is used in trading. Okay, what exactly is a fair value model? So briefly, I think let me talk about this. Okay. So if I take the first setup that I have, I could write this as RT minus, I'm going to write it as RF, that is the risk-free rate, is equal to, write it as alpha plus beta times market return minus this plus epsilon here. Okay. So this is the traditional CAPM model. So what it says is that excess return is related to excess market return. The beta is the risk parameter that you have. And if this model explains completely what is going on, then you should expect generally alpha to be 0. Right? There should not be any excess return beyond what you pay for the riskiness of your asset compared to the market riskiness. So the fair value models are generally tend to be the following. They look at RT minus RF. This is the excess return that you should expect, minus beta times RM minus RF, and this quantity is supposed to be, as per the hypothesis, supposed to be roughly 0. Right? So whenever that quantity exceeds a certain number, that indicates that these returns are becoming profitable. Right? So you may want to invest your money there. Do you follow what I am saying here? So usually I think when you look at the models here, returns we took it as, generally we took returns as completely random, right? And then here we are adjusting for the risk-free return. That means that return should be at least the risk-free return to be in the model. And then now we are saying that further the excess return that you are paying could be further adjusted by the riskiness of the asset. Okay, so whenever this deviation is greater than some number, that means that alpha is positive. So that indicates that this particular stock is doing well compared to the market. Okay, so that's how the fair value models are used. But in all these things, the key point to test is that there is no arbitrage here. That means that you need to test A is equal to 0. Okay, how do you test this one? So this is a test that I want you to note here. So factors are portfolios of traded assets and risk-free assets, or it could be market portfolio, which is nothing but S&P 500 index that you could use. So I think the right hand side is fairly arbitrary. I think people have used all kinds of things before. So here I'm just going to assume that both sides have excess return. Your goal is to check whether that constant A is equal to 0. Okay? The test I'm going to suggest here is given by this quantity here. So there are two things that I want you to note. One is that this is supposed to be the estimate of the intercept, and sigma hat is the estimate of the residual variance. And this quantity here, you can see that z bar plus sigma hat inverse plus z bar is nothing but the average of the predictor variables that is given by z bar, and sigma hat is nothing but the omega hat is nothing but the variance covariance matrix of the predictor variables. Okay. So as I mentioned, in the fair value models, usually if you use CAPM, it's going to be of dimension 1, just only one market factor. And if you use Pharma and French, it's going to be 3 factors. And there are some other factors people use. You can use industry factors and all the other factors. Usually the dimension on the right hand side generally tend to be smaller. You should worry about the dimension on the left hand side. Okay, so you can show that testing for the constant, the intercept term A is equal to 0 can be shown to follow this F distribution. As I mentioned, this is used in the fair value models. Okay, So, where does it, how does it fit here? It fits here in the following sense. Essentially, you're checking whether the C matrix, whether certain columns or rows of the C matrix are zeros. Okay, that's exactly what we are doing. Okay, so you can write this in terms of the factors as I mentioned before. So this is going to be C times xt is given as the first column is 1, the second column is ft plus epsilon t. Okay. So if the first column is the entry in the predictor variable is 1, the second entry is the ft, you can show that what you get is the intercept term as the first row. So essentially you're checking whether the first row of that C matrix is 0 by checking for alpha is equal to 0. You can rewrite this equation in many different ways. Okay. So all of you comfortable with this? You need to, in order to get this alpha being 0, you really have to go through, A being 0, you have to go through the calculation. That's the only way you can do this. Okay. So before I get to this reduced rank regression concept, I want to talk about the time series applications. Okay. So once you have this setup here, how can you use this on autoregression? Okay. So this leads to what I'm going to call as vector autoregression. Let's assume just for the time being you have yt is equal to pi 1 yt minus 1 plus say pi 2 yt minus 2 plus epsilon t. Okay. So this is a m dimensional time series, and this is you can see, because you are lagging, this is also m dimensional, this is also m dimensional here. All these matrices are supposed to be m by m, this is m by m, and this is m by 1. Okay. So here how many lags we are including here? How many lags of yt we are including? 2 lags, right? T minus 1 and T minus 2. So for that reason, this is written as vector autoregressive model of lag 2. Okay, order 2. So you can write it for any number of lags, and you can see that how by increasing the lag, how quickly you are going to explore the number of parameters. Suppose m is equal to 5 series you are looking at simultaneously, it's going to be 25 numbers here, 25 numbers here, right? It becomes 50 numbers. Okay. Can you write this in the form of a regression model? You can do that. This is nothing but, you can write it as, you can put this as pi 1, pi 2, then here you can write yt minus 1, yt minus 2 plus epsilon t. Okay. So by writing this, you can write this as c times xt plus epsilon t. And what is the dimension of c? You can see the dimension of c is going to be m by 2m, and xt is going to be 2m by 1. You see that? Okay. So if you know how to compute multivariate regression, you should know how to compute vector autoregression. Okay. But there is an issue here that I want you to keep in mind. The issue is as follows. Okay? Just briefly, I think we talk about it here. You need to impose the constraint on stationarity. Okay? And the case of univariate case, stationarity is nothing but looking at the roots of a certain equation to be less than 1. Here, since you are talking about matrices, stationarity means that roots of this eigenvalues of this matrix here, or roots of this polynomial, matrix polynomial, should be less than or equal to 1. Okay? So, briefly, I think let me give you an illustration here. We started talking about it last time and we didn't go too far with that. So, just briefly, I think if you can understand this case, I think it should be, suppose you have a univariate model, epsilon t. Okay. What is the condition for stationarity here? What should be the value of pi? Should be less than 1, right, in absolute value. Okay. So, absolute value pi should be less than 1. Okay. But if this is a matrix, yt is equal to pi times yt minus 1, that's epsilon t. What is the constraint here? Now, pi is a matrix, right? It's not a single number. So, you can show that this is same as saying, if we take the eigenvalues of this matrix pi, the eigenvalues should be less than 1. Lambda should be less than 1. Okay. Since pi is a m by m matrix, you are going to get at most m eigenroots, and you can show that those roots must be less than 1. Okay. So, that is a constraint that we are going to use. Same concept extends to AR2 case 2. At the most, we are going to use AR2. Beyond that, I don't think in the financial time series, I don't see much use for more fancier models, yt minus 2 plus epsilon t. Okay. Again, what is the condition for stationarity here? Condition for stationarity is not as simple as I have written here. Condition for stationarity is that lambda squared minus pi 1 lambda minus pi 2 roots of this equation. I think roots of this equation should be less than or equal to 1. So, that is the constraint we have. Okay. The same concept goes through for the AR2 process too. If you have an AR2 process, yt is equal to pi 1 yt minus 1 plus pi 2 yt minus 2 plus epsilon t. So, the idea here is the same idea goes through. I am going to write it, I'm going to write it in a slightly lambda squared minus pi 1 lambda minus pi 2. Roots of this matrix polynomial should be equal to 0. Okay. Or sometimes you can write it in the following form. Can you write this as a AR1 process? You can do it. Or you can write it in the matrix form and then go through the calculations to get the eigenvalues and eigenroots. One simple way people write is as follows. Okay. So, once you know AR1 case, you don't have to worry too much. That's the reason I want to write it in the following form. So, I'm going to write this as yt is equal to, just for the sake of illustration, I'm going to write it as pi 1, pi 2. Here I'm going to write yt minus 1, yt minus 2, plus I'm going to write epsilon t. I'm going to do some simple trick here. I'm going to write yt minus 1 here. Since yt minus 1 is exactly here I, I'm going to put it 0 here, this is 0 here. This is nothing but just creating an artificial system here and write it in the form of this. So you can show that this matrix here is like the C matrix, and you can show that the eigenvalues of the C matrix should be less than 1. Okay? So once you know how to get these things, it should be fairly easy to do the calculation. Sometimes this type of writing, this is known as companion matrix. Companion matrix. Okay. Okay. So the main point of this is that if you can understand what goes on with the vector autoregressive model of order 1, you can pretty much write everything in the terms of order 1 matrices. Okay? So before I get to the rank condition, I want to show you a small data set. It is one of the celebrated data sets. I thought I should briefly go through that, and if I can get Minitab to work. We will be working on a practical data set for the second assignment, where you will do somewhat similar calculations that I am going to do here. So this is a data set that's used in almost any book that you see on multiple time series. Okay, this is supposed to be annual data for, I should have put the years here, 1845 to 1926 or something like that, and this is taken from a monograph by Connolly. I think that is the first book ever written on multiple time series modeling. So if you look at it, I want you to focus on the first 5 numbers here. One is supposed to be the hog supply, and this is the second is the hog price. Next is corn supply and corn price, and the wages. Okay, so there is a interesting theory behind this 5 numbers. Okay, most of the corn that is produced is supposed to go as a hog feed, right? And wages, I think you'll see the 5th column there is supposed to be another input. Okay, so usually they take it as wages is the labor input, and corn supply is more as a other input that goes into hog production. Okay, and these are all, I think I took the log of it and did some analysis. These are not the exact numbers. Okay, and this is the annual data. Okay. I want to show you the pictures of these things on a time series plot, and I want you to tell me the characteristics of this plot. Okay. Suppose I do the time series plot. Hog supply, hog price, corn supply and corn price and wages. And I don't have the time scale, but I'm going to put all the graphs in one page. You can see what you see here. So this is the graph that you see. Okay, these are the 5 series that you have. Do the series look stationary or non-stationary? Almost all of them look non-stationary. Can you see that? Okay. And the question, I think, is that do you see any of the series moving together? That's a concept of co-integration. Okay. They are non-stationary, At the same time, do you see any of them moving together? Okay. I can try to plot them on the same graph. I think some have a little bit higher scale, so they may screw up the other graph. Let me try to plot this on the same graph. Roughly, that's a graph that you see. Okay. So the top graph is supposed to be con supply, and then the yellow thing is the wages, and then you have all the other things going around here. Can you see that there is some sort of joint moment here, somewhere here? The series are clumping together, right? Before I get too much into this thing here, why should we worry about modeling this series together? Why not we model each one individually? So if you want to predict what the hog price is going to be into the future, you can model hog price as a function of its past, right? And use a univariate model to predict into the future. That's one option. Or you can use the hog price in addition to the past, its own past. You can also include other factors that may influence the hog price, right? That's one way to do it. Okay. What is the advantage of doing these things in the form of vector autoregression? See, essentially what I'm asking is that what is the difference between univariate modeling and multivariate modeling? So let me write this here. Okay, there is a whole course can be taught on this kind of topics. So I'm trying to give you some simple intuitive ideas here. Univariate versus multivariate modeling. What is the main difference? So usually multivariate modeling tends to give you better forecasts because you are using more information, and instead of modeling univariate, taking one series trying to figure out what factors can influence it, you can include part of, say if you are going to predict hog price, you can include con supply and con price. Maybe wages don't make any difference, you can just drop the matter there, or you can do many other things that you think are important. But if you model them jointly, I think you can take into account indirectly the constraints that may exist among this coefficient matrix. Okay? So the preference for multivariate modeling is that first of all, I think you get parsimonious models. Okay? You get somewhat simpler models when you use multivariate regression. And the second part of it is that better forecast. So those are the two reasons why you want to use it. Okay, and here I also looked at, I think I kept this 5 lag 1 variables to see how good they are. Just to show you, I'm going to take the hog price, and you will get very high correlation, mainly because hog price is non-stationary. So hog price versus, I'm just going to hog price 1. Just want to keep it simple, so I'll just put. So that's a model that you see. Okay, so can you just briefly, I think I'm going to write here hog price is given as 0.574 plus 917 hog price 1, that is lag 1, and R squared you can see is roughly 80%, and hog price coefficient is significant. Can you see that 0.00? P values are significant. Okay. So essentially the model I have here is that hog price is equal to, the constant term is not significant, you can 0.574, p-value is 0.103, but this is given as hog price at time t is 0.92, hog price at time t minus 1. So that is the model that I have, and R squared is given as 80%, 0.80. Okay. You can see that this 0.92 is almost 1, right? So it's a non-stationary process. Okay. But suppose I include other lags, see whether that makes any difference. So this data I have posted on the coursework, you should be able to play with this hog price 1, and I'm also going to include hog supply 1, corn supply, corn price and wages. See what do I get. So when I go through this, what kind of R squared I'm getting? 92.6. Obviously including other information seems to help. Okay, but you also have to be careful. Getting a very good R squared at model fitting doesn't guarantee it's going to be good for validations. You have to balance between the two. So obviously including other information seems to make some difference here. Okay, so that is the essence of multiple time series modeling. So we'll talk about this a little bit more next time. Okay, and we can go from there. The key part of it is that you can also see the hog price coefficient is 0.20791. So that nonlinear component that you saw in the first part of it is probably coming from other variables too. So that's how we are going to look at modeling the non-stationary series. Okay, so I'm going to stop here, and if you have any questions, let me know. I couldn't get to co-integration, but we'll get to it on Wednesday. Okay.